Hello. In this lecture, we'll discuss pumping lemma for context-free language. So, if L is a context-free language, then there exists P, where this P is basically a pumping length, such that for a Z or a string belongs to the language L, if length of this string is greater than or equal to P, then there exists U, V, W, X, Y such that Z or the string is or E string can be partitioned into 5 parts: U, V, W, X, Y. So the conditions are length of V, W, X should be less than or equal to pumping length. Number 2, length of Vx together is greater than 0. Both V of x simultaneously cannot be 0. 3, for all I greater than or equal to 0, U, V, I, W, X, I, Y belongs to the language L. That means V and R, X can be pumped. So this is the formal concept of the pumping lemma for the context-free language. Now we have to prove this pumping lemma for the context-free language. So proof. So let G be a context-free language, and we assume that this context-free language is in Chomsky normal form or CNF, such that language generated by this grammar G is basically L. And also further we assume or let that Z be a string, and it is a very long, Z be a very long string in L. So in the language L. This very long means we want to repeat at least one variable from the start, that means root, to the bottom of the parse tree. That means if we draw the parse tree, it will be look like this pyramid structure, and this is from the root. We assume that from here to bottom of the tree, this is the longest path. So it is within this long path from root to bottom, that is leaf node, at least one variable there is a repetition. So we assume that a be a variable that repeats. So a appears somewhere else again. Okay. So we assume that this is suppose this is a, within this longest path, this a is basically a variable that is repeats. So a appears somewhere else again. So a again, suppose we assume that it appears here within this path. So when we consider that Z be any string and it is very long, and this string belongs to the language L, and our desire is that at least one variable there is a repetition from top to bottom, and we assume that A is a on variable here and it repeats anywhere in this path. We assume that this here, this variable A, there is a repetition. Now a long string must have a deep parse tree, as we know, a deep parse tree, and which in turn means a path with a repeated non-terminals, as we have mentioned here. So longest path in this tree by the pigeonhole principle must have some variable. We mentioned that this is a repeat. Now uh, we take P, that is pumping length, is equal to 2 to the power k, where this k is the number of variables. Okay. So consider Z be a string that belongs to this language L, such that mod or length of that string is greater than or equal to this pumping length, which is basically in terms 2 to the power k. Right. Now consider a path. Consider a path or parse tree. Consider a parse tree for this Z, right? Now height of this tree is at least k plus 1, and parse tree and a parse tree for Z has a path of length k plus 1. So if we consider, suppose we consider a context free grammar, suppose S to AS or A, or A to SA or B, which is already in CNF or Chomsky normal form. Now if we want to find parse tree for the string, suppose AB BA, right? So it will be look like this. The parse tree will be S to AS, and here this A will be replaced by S A, and here it will be A and S, and this will be A terminal, here it will be B, here it will be B, and here it will be A, right? So these are basically the node of the parse tree. We consider this. Now as in this grammar, the number of variable k is equal to 2. So the longest path, so here we consider this path is the longest path, right? We consider this path is the longest path. Obviously all paths are same length, so we consider this path, right? Now the length of this longest path is obviously k plus 1, that is 3. 1 2 3. So length of path, longest path, is equal to k plus 1, which is basically 3, and vertices on this path is basically k plus 2, which is basically the 4 S, A and B, and the internal node will be k plus 1, that is 3. That means A is basically internal node, and here the vertices on this path is basically 4, one of which is a leaf vertex, leaf node or the leaf node vertex, and remaining is a 3 vertices which are basically the internal node or the vertices. Now, as we have mentioned that a path, that is a length k plus 1, so length of the path k plus 1 has k plus 2 vertices, right, out of which at the last one is the leaf node, that is labeled by the terminal. As we have mentioned, it is labeled by the terminal. Thus there are k plus 1 internal vertices on this path. Now there must be two vertices, we say, that is n1 and n2 on this path and have the same level, and we say it is a. We say that it is a. And n1, we say that is it is n1 and it is suppose n2. We consider it is n1, n2. And n1 is the ancestor of n2. Okay. And already we have considered that the string is z equal to a b b a. So length of this string is basically the 4, which is greater than or equal to 2 to the power k, that is the p or the pumping length, which also satisfies this condition. K is the number of variables, so 4. So as we have mentioned that it basically forms a pattern like a it basically likes a pyramid structure, and the yield, and also we consider that yield of the tree rooted n2, that is n2 bw, we consider that it is w. So we consider this yield rooted at the node or rooted at the vertex n2 is w. We consider that it is w. Yield, actually yield, and yield of n1, that is this n1 vertex or n1 node b, we consider that it is v v w and x. So we consider it is a v. So now we can write in that way also that this portion we consider that this is w, and a, from this a we consider that it is from this n1, the yield is basically we consider that it is v and it is w, and also on the right hand side from this node, as actually there is nothing, so we can consider that on the right hand side it may be x. So we consider that the yield, now I write here again the yield of the tree rooted at n2b, so n2 it is w, that is yield, and yield rooted at n1 is v, w and x. Then yield of the root, that is z, it will be this portion. So s, here it is basically from starting from the root s, so yield of root we say that is z, is we can write it that is u v w x y, we assume that it is, we say, so it will be u v w x, and its right portion, that is from this portion we consider it is y. Okay, now again we can consider in this way that it is our first tree, Okay, we consider that it is our parse tree. And now there is a longest path from here to here, suppose from this root to bottom of the tree, and within this path, suppose there is a variable a, and there is a repetition of the another same variable a here. Okay, now we so this a or bottom of this a contributes to this language something a, and this a also contributes to the language something, right? That is bottom a, or another way we can say that as the variable a repeats, so cannot be a start variable. So this a is basically is not a start variable, rather it is a start variable. So start variable, which means a itself must generate something of the string, because we consider that from here it is a string z. So this a generate something that actually belongs to this string, and bottom of this a, or actually this a also not a start variable, so it also means something of the string 2, or it also makes something of the string 2, at least one character, right? So actually we are basically part this string into a different pieces. So we name this, it is, we can consider that it is u, it is v, it is called w, it is x, and it is y, right? Now so height, now height of this, height of n1 can be assumed to be at most k plus 1. Okay? So thus yield of n1, that is vwx, is at most 2 to the power k, that is a p. Okay, so here that this is n1, so it is v, w, and x, and height of n1 can be assumed, to assume that at most it will be 2 to the power k, or yes, or it is a pumping length which is p. Since the grammar has no null productions and no unit production, so since the grammar has no null production and no unit productions, so obviously this vwx which is not equal to w, and hence, or that is v and x together length should be greater than 0. Both of these simultaneously cannot be 0. So now based on this parse tree for this string z and the definition of u, v, w, and u, v, w, x, and y, what we have obtained, we have a, there is a parse tree for this string z. There is a parse tree yield, parse tree with yield. With yield basically, as we know, this u, if we consider this u, a and y, u, that means this a, or we can mention here particularly this a, so u, a, y. So there is a purse tree with yield u, a, y, and root is s. And here we not expanding this n1. So also you can write here not expanding n1. So what we have obtained after many steps is drives u, a, y. That means from here this is a, this is start, and we consider that u, and it is y. It generate this. Obviously there is a parse tree with yield. There is a parse tree with yield uh, v, a, x. It means this v, a, x. So that is a parse tree with yield v, a, x and root a, that is n1, and not expanding n2. Here this v, that means this v, a and this x, and we have not expanding this n2. If we consider that it is n1 and it is considered, suppose it is n2, then v, a, x, and without expanding this n2, so we have obtained v, a, x. That is a, after many steps we can derive v, a, x. And also there is a parse tree, yield w and root a, that is n2, is a drives w. Here this a, that is n2, so this is n2, so it basically derives this a derives w. Now putting this all together, so putting this, that means this as well as this together, so putting together we have s stripes u, a, y. Here s is the root. We have considered that s is the root, and without expanding n1, without expanding this n1 here, without expanding this n1, right? Now after few steps, this a, or by considering this a as a root, so u, then there will be v, a, x and y. Here this a is basically n1, but without, here the root is a, which is basically n1, and without expanding n2. And if we repeat this, then it will be look like this: U V V A X X Y. That means we substitute this by this, and ultimately what we obtain: U V to the power I A X to the power I Y, and finally it gives U V to the power I W X Y to the power I Y. Here this A, that means N2, which basically gives W. So this, and this language that should be belongs to the language L. So that means we can pump B to the power I or X to the power I for I greater than or equal to 0. This should be belongs to the language. So this is the proof or how basically it constructed. Now we'll give an example. Example, suppose B is a language of the form A to the power n, B to the power n, and C to the power n, such that n greater than or equal to 0 is not context free language. So to prove this, initially we have to assume that B is in context free language. So assume B is a context free language, and let P be the pumping length. Be the pumping length. So let S, we consider S is equal to A to the power P, B to the power P, and C to the power P. So length of this string will be 3P, which is greater than of the pumping length P. And the pumping lemma states that S can be pumped. Clear? Pumping lemma statement says that S can be pumped, but we show that it cannot be. So in other words, we show that no matter how we divide this S into divide this S into U, V, W, X, Y, one of the three conditions that we have written here, one of these three conditions of the lemma is violated. So we have to, and then that means there is a contradiction, and hence we can prove that it is not a context-free language. Now there will be two cases. So number one, case one, when both V and X contains only one type of alphabet, only one type of alphabet symbol. That means V only contains either A or V only contains either B, not mixing. Similarly, X contains either A, B or C, but cannot mix. Right? So now we for case one, we consider that suppose n equal to 4, right? So the string will be of this A, because A to the power n, A, B, 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 and C, 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 C. Right? Now we consider that this is U and this 2A is V, and from here to this it consider it is W, or we consider it is UVW, it is X, and we consider it is a Y. Right? We can partition anywhere. So now the case one, as we have mentioned, that V and X contains only one type of symbol. Now for I equal to 2, as per the pumping lemma, U, V2 W X2 Y should belongs to the language L, should belongs to the language L. But what we have obtained, U is basically A, V is A, so it will be repeat. Then W is A, B, 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 C. So it is U, it is basically V2, it is W, and X2 means CC, so it is X2, and Y means also CC, it is Y. Now what actually we obtain? So language pattern A to the power 6, B to the power 4, C to the power 5. But as per our language, same number of A followed by same number of B is followed by same number of C. So here it does not satisfy. So it does not belongs to the member of the language L. Hence is not context-free language. There is another case that may occur, case 2. And in case 2, the situation is that when either V or X contains more than one type of symbols, contains more than one type of symbol. Yeah. So in this scenario, what happened? So here also we consider that we can partition A, and B, 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 C, 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 C. We partition this string into UV like that. Suppose this is U and contain more than one type of. So we consider that this is V and consider this is W and it is X, more than one type of symbol, or we will consider that is Y. Okay. Now for I equal to 2, it will be look like this. A U, that means A, V2, that means A, B, B, again A, B, B. This whole thing is basically V2. Clear? It is U, and W means B, where it is W, and X is basically BC, so X2 means BC, BC, so it is X2, and finally Y, that is C, 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 it is basically Y. So look, it contains 2, 4, 5, 6, 6A, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7 B's and this is. So obviously this pattern does not belongs to this language L, and hence is not context free language. So in this way we can prove that certain languages are not context free languages.